Okay, I'm going to do an example of a proof by induction of a finite series. So just remember for induction, the first step is to show that n equals 1. Then you want to assume that n equals k holds, where k is some number, usually an integer. And then we show that n equals k plus 1 hold. Okay, so this is the basis step. This is like sort of like the hypothesis, and this is the induction that's going on. Now, first, we're going to do the n equals 1. So we're going to do step 1, which is we're going to show that n equals 1 holds. All that means that if we substitute 1 into this series here, this is like a finite sum, that means I starts at 1, and it actually also ends at 1. So I'm going to put n equals 1 here, which means that this thing is just, for the first one, it's 1 times 1 plus 1. Since it starts at 1, it finishes at 1, it's already done. So this thing, this series notation, and where I put i's, you put the I for 1, and then it's just, there's only one step to it. So then all we're going to do is plug 1 into the ends here, and I'm also going to color code that. So you see I have the 1s here. Now I'm going to check, and I'm going to show that n equals 1 holds. I'm just going to confirm that this sum, which is, it's only one part of it, is equal to that. So we'll simplify both sides. So simplifying at first gives you, this one is just 1 times 2. This one is 2 plus 6 plus 4 over 6, because 1 cubed and 1 squared and 1, that's all 1. And then this right side further simplifies into 12 over 6. And then 12 over 6 happens to be 2. And this is also 2. So since those are equal to each other, check. So n equals 1 holds. So we've done our basis step. Now we're going to move on to, we're going to do our assumption, our hypothesis, which is step 2. And we're going to assume that n equals k holds. So holds to be true. So in other words, we're assuming that in this infinite series, if we plug a k into here, that this will work out. So if I assume n equals k holds, that means that if I have, using my little sigma notation, if I start at I equals 1, go to n equals k of I times I plus 1. All right, if I do that for k, here's what it's going to look like. The first step is 1 times 1 plus 1, and that's it. But then you go to 2. Let's assume that k is a number like much higher than 2 even. Plus, so the next thing you go is 2 times 2 plus 1. All right, plus, and then dot, dot, dot. It could be 3 times 3 plus 1, 4 times 4 plus 1. It keeps going further and further. And you stop once you get to k. And you do k times k plus 1. So that's why this index starts at 1 and goes as high as whatever k is. So we're going to assume that this holds true, that it is true that this is equal to, instead of putting n squared, so our original thing had 2n cubed plus 6n squared plus 4n, I'm going to put 2k cubed plus 6k squared plus 4k. And again, this is all part of just assuming that this thing, that thing we're trying to prove holds true for k. Now, if it holds true for k, we're going to hope that that's going to lead us to the fact that it holds for k plus 1. So we want to show that n equals k plus 1 works. We can't assume this, but we want to, using this step right here, I'm going to do a little substitution. So I'm going to try to find this somewhere in this thing with the infinite sum, and I'm going to substitute this into it, okay? So writing in sigma notation, instead of just k, I'm going to do it for k plus 1 here. So if you rewrite the sigma notation and you do it this way, it'll still start at 1 times 1 plus 1, because it starts at 1 no matter what. And plus, say it keeps going higher, 2 times 2 plus 1, dot, dot, dot. And then it even goes up to k times k plus 1, but k is no longer the max number that you stop at. K plus 1 is the max number. So this one just goes one step further. So k stops here, but notice how that's going to be contained in the k plus 1 case, but you got to go one step further. You got to do k plus 1 times k plus 1 plus 1. So I'm going to highlight to show you what's going on. In the previous example, k was our max, okay? So we stopped at k times that number k plus 1. Well, here, k plus 1 is our max, so I'm going to highlight that blue. So when I highlight it blue, you can see that there's just one more term because you're going one higher. Now, here's what I want to happen. I really want, what I want to show is I don't know that this is equal to what I want it to prove it to be. What I want to prove it to be is this comes out to, instead of putting a k here, I want there to be a k plus 1 here. So everywhere there's a k, I would like there to be a k plus 1. So, or like just like before, where there was an n. Remember, the original thing is n, and I would like k plus 1s to go all there to show that it works for our k plus 1. All right, I'm going to have trouble doing this directly, so I'm going to show you. We're going to do as far as we can, and then we're going to do a little workaround to actually go backwards in this thing. But first of all, let's substitute. Again, using our little induction here, the induction hypothesis, I'm going to take this red part, which is the same equivalent to this, and so I'm going to substitute that here. Okay, so here I'm going to substitute, since this stops at k, I can just rewrite this term. And so I just transpose this, rewrite this down here. Now, I would like this somehow to, just like this is this same red part as this right here. I would like to combine it with this right here, but this thing has a denominator of 6, like after we substituted. This thing doesn't have any denominator, so that's unfortunate. So I would really like there to be a denominator. But first of all, I can simplify this. So you notice how this part right here is, this is a k plus 1. And then this k plus 1 is really k plus 2. And then I'm going to go ahead and distributive property this. And so when I do that, you may have heard this called FOIL, but same thing. So I do this. It would be nice to combine these like terms. I see a 2k and a 1k. Let's go ahead and make that 3k. And you notice I don't feel like rewriting this term, so I'm just like, I'm putting these little symbols to carry it down until I'm done with it. But here's the thing. I know that I can't add this, which has a denominator of 6, and this, which has, think of this as having a denominator of 1. If you divide it by 1, I'm not doing anything, so that's completely fair. So here's what I'd like to do. I'd like to have a common denominator. Well, what's your common denominator between 6 and this? Again, this acts like the denominator of 1 there. Well, the common denominator is 6. So I'm going to multiply by 6 on the top and the bottom. Okay, and then I'm going to distribute this 6, and then I'll rewrite this fully. Then I'll be able to add. So I just rewrote this one. Again, instead of recopying it each time, but this time I decided to rewrite it. This one, distribute this 6 to the top. So that's what we got, 6k squared, 18k, 6 times 2 is 12. And then the 6 times the 1 is a 6. So now they have a common denominator. So that's convenient because now I can add them together. So there's only one 2k cubed term, so I'm just going to write that. There's a couple 6k squared terms, so that's convenient. So I'm going to combine, and I'll go ahead and I'll highlight those just so we see what those are. Those are both green. I can combine those. I can combine the 4k with the 18k. So I'm going to go ahead and combine those right now. And so I just combine, simplify, and then instead of writing, they're both over a common denominator of 6. So I just write one denominator of 6. So what that is there's a denominator, if a over 6 plus b over 6, that's just a plus b over 6, where this is a and like this thing is b. So that's all I did there. Now, I am not talented enough to show that this is somehow equal to this. So I'm going to show you a little workaround. Instead of going directly, like I can't get from here to here, but let me show you like sort of a little cheat. So pretend like we just kept carrying down these equal signs the whole time. We were trying to show that this is equal to that. Well, let's pretend like we're really talented, and instead of working from forward to the back, let's work from the back to the front. Let's expand this thing and somehow turn it into this one, and they'll meet in the middle, and we can hide that we did that and make it look like we did like a fancy factored by grouping and we were really smart. So let's take this thing and expand it, and I use Pascal's triangle. So the k plus 1 cubed, you don't have to use Pascal's triangle, but here it is. If you do k plus 1 cubed, here's what it is. It's 1k cubed plus 3k squared plus 1k plus 1. So, and then the 2 is in front of that. So the idea is it's 2 times, and then I'm just going to rewrite this k plus 1 cubed. And so, and again, these coefficients, the 1, the 3, and the 1 came from Pascal's triangle. That's just a shortcut to do it. You could do it manually by, foiling and then foiling again, but this is just a quicker way to do it. Now I'm going to do it with the 6k squared, and this one comes from the second row of Pascal's triangle because it's the squared term. And so I'm going to write down the 6, and then k plus 1 squared is k squared plus 2k plus 1, which is easier to just do by yourself, but it also could come from Pascal's triangle. Notice how 1, 2, and 1, 1, 2, and 1 are the coefficients of those numbers. And then 4k plus 1 is just simple distribution. It's 4k plus 4. And so I'm going to distribute the 2 to these parts, distribute the 6 to these parts, and then combine all the like terms. So all I did was distributive property there. So here we have this thing, and still these things don't look quite the same. I'm not talented enough to show these are the same. And now one thing I was forgetting, I tend to forget this a lot, there's the over 6, right? It's all over 6, so all of this is over 6. Again, all of this, that's just the numerator. This is over 6. I'm not talented enough to figure out how this is the same as this. So since I can't work it forwards, I'm going to continue working backwards by, let's combine like terms right here. So I decided to circle all the like terms. And actually, I noticed something wrong. So everything will check out. I made a mistake at this point. See if you can tell where. Okay. There's the 2k cubed that checks out. And then, I get 2k cubed plus 6k squared and 6a squared is 12k squared. Oh, magically, it's the same thing as this. And then this 6k, 12k, and 4k, 6 plus 4 is 10, 10 plus 12 is 22. Oh, wow, magic. I get a 22k. That's exactly what I got on this side, like they're lining up. Plus, but here I get an 11. 4 plus 6 plus 1 is 11. So that means I must have done something wrong. The proof isn't wrong because they're telling you to prove it. So it means that at some point right here, I forgot to multiply the 2 times the 1. So let me write a 2 there. So these match up. And since these are equal to each other, that means my proof is essentially done. Now, if you want to look smart, here's what you do. You do this. You make it look like you factored this. So the path that this thing takes is you're traveling down here, and then you travel up here, and then you show that that's equal to that. So if you want, you could go ahead and rewrite these pieces right here, and I'm going to show you how to rewrite this. Okay, I'm just going to take it and drag it. Okay, so I'm going to grab this part and put it under here, and then this part and put it under that, and then this part and put it under that, and then show that this is equal to that, and it makes it look like I was way smarter and I knew how to factor this when really I didn't. So let me show you really quickly how I move those. So I'll move that part over here, okay? Made it look like I did that in this order when I did it backwards. Now I'm going to move this part under that, okay? And then I'm going to move this part under that. Okay, so I'll move that there. And then, and of course this simplifies. This comes out to the thing that we're trying to prove. This comes out to 2 times k plus 1 cubed plus 6 times k plus 1 squared plus 4 times k plus 1 all over 6. And then I'll just make it look like I didn't do. You can choose to erase your work, to kind of hide it. But all of this just keeps getting carried down all the way down to here. I'm just going to go and rewrite it. I'm going to rewrite it for the second version right here. And since we have equality, we just showed that k plus 1 holds if the k step holds. And since we showed that 1 holds, well, that means pretend like 1 is the k. Well, if 1 holds or if k holds, that means k plus 1, which means 1 plus 1, which means 2 holds. All right, well, then 2 holds. Well, if 2 holds, then 2 plus 1 holds, which is 3. Oh, if 3 holds, 3 plus 1 holds, which is 4. There's your proof by induction. So you can review this. I'll have a PDF version of this linked in the video description through a Google Doc so that you can look at exactly the steps one step at a time. But this is your proof by induction. We started here. We went down to here, and remember, we hit a dead end. We showed all that stuff. We actually hit a dead end right around here. And then all the stuff, we're going to start from the bottom up. We did the rest of the stuff completely backwards, but we made it look like we did it forwards. We made it look like we're really smart and we somehow knew how to factor and separate this. So, but we made it look like we were smarter than we were. That's it.